Good morning, everyone. I'm Chunhui from the Second Institute of Oceanography, China. Firstly, I want to say thanks to the IC for the invitation to give this presentation on the topic of new approach to deep-sea polymetric sulfide exploration. My talk will contain the following four parts. Firstly, I would like to give an overview of the exploration method in the use for the sulfide. As we know, hydrothermal circulation systems have been developed at middle ocean ridges of different spreading rates around the world. Most of them are tectonic and magma controlled and have great potentials for the mantle mineralization. Around 60,000 global middle ocean ridge, there are spread quite a few black smoke hydrothermal fields with above 300 degree high temperature. According to the database of Interridge, there are more than 300 vent fields visually confirmed, and further more than 300 active fields were inferred according to the water column plume surveys. How to find more sulfide deposits and how huge the deposits could be and what is the associated environment issue are our main concerns. At this slide illustrates an overview of the exploration process, which could basically be separated into three steps. Firstly, we do the mineral prospective mapping, which is mainly based on the mineral prospective model, including magma and topography. This method will help us to realize the area and locate prediction. Secondly, with the help of prospecting factors and the detected technology, we could delineate the anomaly along the ridge for the plume, alteration, fauna, and finally, we use various tools like TV-grab, RVHUV to verify the anomaly to see if they are really vents or sulfide related. Next, I would like to talk about more details about how to detect and estimate the source of SMS deposits. The first approach I want to talk about is the plume tracing. As we know, the turbidity, methane, dissolved Fe and Mn, and ORP in hydrothermal plumes are important groups for searching sulfide deposits. Deep-tool system with integrated multi-parameter sensors can be used to obtain hydrothermal anomalies from tens to hundreds of kilometers in multiple layers of water near the bottom, and to observe anomalous information about the seafloor together with the distribution of seafloor funnel by camera. And that's why in recent years, the first step in the exploration of sulfide deposits is usually the checking of the hydrothermal plumes. Equipment has developed for deep plume tracing to precisely locate the vents, like the AUV and the glider. With the help of this advanced equipment, the detection efficiency of hydrothermal anomalies has greatly improved in recent years. Equipped and integrated with multi-parameter sensors, AUV are also capable of acquiring high-resolution topographic data, as well as taking pictures of the seafloor. Another very useful approach is the geochemical tracing. Similar to the land mineral exploration, Geochemical prospecting is also an important approach in seafloor sulfide exploration. Through geological sampling, we can obtain the information of the distribution of mineralization elements in the seafloor sediments, making it possible to trace hydrothermal deposits and even sulfide deposits in different basement rocks. Once we have a rough estimation based on the anomalies, we could take use of the submersibles such as the manned submersible Jolong and the deep sea Wally and the ROV Sea Dragon to carry out the detailed survey of the hydrothermal fields. The obtained distribution characteristics of hydrothermal to obtain fine-grained environmental parameters of the hydrothermal fields. For the resource estimation of the sulfide deposits, several geophysical methods have been used to access the resource. One typical and efficient method is electromagnetics. First, we developed one digital TEM system to explore the resistivity structure below the seafloor. The acquired data reveals sulfide deposits on the seafloor as low resistivity zones. Another electrical magnetic method, such as the CSEM, is also widely used for the resource estimation. Self-potential and reflection seismic are also effective and high-resolution geophysical methods. The seismic data based on our velocity model indicates a layered internal structure of the sulfide. A more simple method is the self-potential, which measures the distorted electric potential derived by the natural current internal of the ore deposits. The electrodes can be easily mounted on the AUV and other platforms. We once carried out some novel SP tests at Yuhuang deposits under SWIR, while the marine self-potential topography reveals an ore with 65-meter thickness below the seafloor. Magnetics is another efficient way to estimate the deposit resource. High-resolution magnetic survey of SMS is typically operated by the AUV or ROV. It mainly focuses on the mechanism of the magnetic anomalies and mapping the boundaries of the hydrothermal alteration. We developed our high-precision near-bottom magnetic system based on the AUV and characterized the 3D structure of the SMS according to the magnetic data. Besides, seafloor drawing is a basic and accurate method to obtain the sulfide boundary for exploration. In this regard, it has been well practiced in the TAG or swallow areas. In Yuhuang deposits on SWIR, we obtained about 30% copper-bearing sulfide cores, which reveal good resource prospects. The third part, we would like to discuss monitoring of hydrothermal circulation system. Here, we refer to the long-term monitoring of hydro systems, including heat sources, fluid channels, and mineralization processing. as well as the environment of the venting. Refer to the heat source, thick crust, and magma chamber was identified beneath the torrential hydrothermal fields in the southwestern ridge for the first time. This is rare along the ultra-slow spring ridges, which are relatively lack of magma supply. Then we need to figure out where is the heat source and how was it driving for the launch venting. To answer this question, we carried out long-term passive seismic and combined with the numerical simulation. We proposed mental heat convection driven hydrothermal circulation module on the ultra-slow spring ridge. In this module, we think the origin of the hydrothermal circulation at the ultra-slow spring ridge is much deeper than the other middle ocean ridges, reaching below the borehole surface. In addition, the simulation of the mineralization process of the hydrothermal system was carried out, and the related open software app of simulation program was developed. We also released the state-of-art numerical modeling methods and toolbox, include hydrothermal transport model and thermal hydrochemical model. Besides the OBS, in-situ long-period observations of the vent area can capture distinctive phenomena that cannot be detected by the other observation. This slide shows the typical sampling equipment for ecological monitoring. A number of different-sized approaches were applied to sample different environmental and biological factors. This work recovered phytoplankton, zooplankton, meiobenths, micro-megabenthos, water column structures, and current dynamics. About the environment outside the hydrothermal field, the mooring system can monitor the spatial distribution of the hydrothermal pool by obtaining long-period parameters such as the physical properties, temperature, salinity, turbidity, and bottom current, even acoustic monitoring for whales. We have developed 8 mooring systems in the southwestern ridge, with one deployed over 1 year. At the end, I would like to share my ideas about the challenges. As we know, the exploration method for active hydrothermal fields are gradually maturing, while the number of inactive sulfide fields is relatively low. For this inactive or offshore sediment covered sulfide deposit, we need to figure out how far they are. We need to figure out how far they are, how many they are, and more important is how to explore them beside the SP system. This is still challenging for now. Deep sea exploration has been constantly innovated in recent years. I just showed the 3 Dragons system from Comoros, which have made great work for sulfide exploration. Safe and green exploitation for sulfide resource may come true one day in the future in the promise of continuous innovations and effects. The last but maybe the most important challenge is how to balance the resource exploitation and environmental protection. the structure's stability, environment, biodiversity of hydrothermal system are some real concerns for now, and we should focus more on the long-term in-situ observation. And to take care of this challenge, I think international cooperation is very important. Knowledge sharing could be accelerate the innovation and create real big progress. And I hope that in the future we could strengthen the cooperation on scientific and technical aspects to promote the development of the sulfide exploration. Intelligent Working Group, several massive sulfide resources along the mid-ocean ridges, is looking forward to cooperate with the environmental experts and ISA. This is all for my presentation. Thanks for your attention.